Hello, everyone, and welcome to Minnesota HIMSS Informatics webinar series. I'm Vitaly Hirasevich, professor of anesthesiology and medicine at Mayo Clinic and host for today's event. And it's my pleasure to introduce today's speaker, Dr. Ted Shortlife. And I would not say anything wrong if I say he's a living legend of the biomedical informatics. He's a chair emeritus and adjunct professor of biomedical informatics at Columbia University. Also, he holds adjunct appointments at Arizona State University and Weill Cornell Medical College. He editor emeritus of the Journal of Biomedical Informatics and also editor of Biomedical Informatics textbook, which is a primer in biomedical informatics. 5th edition was just released a couple months ago. Dr. Shortlife was president and CEO of American Medical Informatics Association and also was founding dean of the University of Arizona College of Medicine in Phoenix. He also formed some graduate degree programs in biomedical informatics in Stanford, Columbia, and Arizona State Universities. He has PhD in computer science, and he is a physician who practices internal medicine. Dr. Shortlife is an elected member of National Academy of Medicine and fellow of American College of Medical Informatics. He also Master of American College of Physicians. He received some this is high award in Association of Computer Machinery, Grace Murray Harper Award in 1976 and Acme Morris Collin Award in 2006. Today, Dr. Shortlife is going to talk about artificial intelligence, biomedical artificial intelligence, roots, evolution, and an agenda for the future. Welcome.
Thank you, Vitaly. Thank you all for joining us today. It's a pleasure to have an opportunity to talk to you and try to acquaint you with a little bit of this history of the field of AI. This is a very big field these days. And sometimes it seems to have just been thrust upon us recently. But it really, like many disciplines, of course, has evolved over many years. I've had the pleasure of being involved in the medical part of that evolution ever since I was a graduate student. So a lot of what I'm going to be talking to you about today is very familiar to me since I kind of lived through it. And I hope you find it interesting. I'll try to be done in time to allow you to press me with any questions you might have before the end of the hour. My goals are to make it clear that what's happening today is really part of a 50-year trajectory of the science of artificial intelligence. It's still evolving, and the medical part of it goes back almost to the beginning of the field. I'd like to provide some advice to those of you who do biomedical AI, either as researchers or implementers, drawing upon the experience of that last 50 years, and summarize where we are today in the evolution, make some observations about what it may take for us to move smoothly into the future in this area. But we're certainly going through a bit of a whirlwind at present, as most of you know, and I will certainly be commenting on that as we proceed as well. So let's go to the beginning. Many people would say the field of AI started at a meeting at Dartmouth in 1956 when a bunch of computer scientists got together who were interested in whether or not you could really simulate the human mind and human problem solving using computers. And it was John McCarthy, pictured here, a much more recent picture than 1956, who coined the phrase artificial intelligence, and of course it's stuck ever since. And although there have been a few efforts to get us to change the name of the field, I don't think that's going to happen, and AI is now deeply part of our culture. But in Europe it was called machine intelligence initially. We've heard efforts to call it augmented intelligence, but for today let's just call it AI, artificial intelligence. Arguably, it was Alan Turing who really foresaw some of what became the field of artificial intelligence, although he never used or heard that term himself, since he was another decade or so earlier. Now, many people today think that it's all about machine learning, and I want to make it clear that machine learning is not a recent phenomenon. Machine learning goes back probably at least to the late 1950s, when this fellow named Arthur Samuel, who was at IBM Research, got interested in getting a computer to play checkers and to play it well. And of course, he knew a bit about how to play checkers and kind of wrote the rules and goals and tried to teach his program the game. But after a while, he realized that he wasn't good enough at checkers to make the program as good as he wanted it to be. But the program did know how to evaluate what it was doing. And so he made two copies on two computers, had them play against one another. It went on for hours and hours and hours. They learned strategies and tactics in the process. They changed their various scoring functions. And eventually the program, the kind of merger of these two that had been playing against each other, became unbeatable. And even experts in checkers were unable to beat this computer program that had basically learned how to become a world-class expert. So that's a little hint of how early on machine learning was part of what was this emerging field of artificial intelligence. But obviously it didn't explode in the current way until quite recently. And we'll talk in a while about why that's true. In the 1960s and the 1970s, there was a lot of AI work that was going on at the major universities that you would find familiar to us today. It was just a lot earlier. Certainly machine learning and early work with neural networks, natural language processing, trying to understand human speech in those early days, and a large amount of effort to try to simulate human problem-solving behaviors. Now, medicine was one of the areas in which some of this work was done very early, in fact, starting in the 1960s. So medicine was a driving force behind much of the applied aspects of artificial intelligence research development. And of course, because medicine was tricky and not well understood in some sense itself, some of the methods that were developed for medical AI ended up feeding back into the field of AI itself. So there was a lot of synergy between the work in medicine and healthcare and the basic research in artificial intelligence in those early days, most of which went on in engineering schools and computer science departments. I would say during the 1960s, there were three institutions that were the leaders. They were all in the United States at that time. Of course, today AI is a global phenomenon, but it was Carnegie Mellon. Actually, Carnegie Mellon was known as Carnegie Tech early in that decade, but was renamed later as Carnegie Mellon University, and MIT and Stanford. The Carnegie Mellon leadership largely was these two people. Many other names could be on this slide, but if you think of CMU in the 60s, you think of Herb Simon and Alan Newell. Newell and Simon wrote many papers together. They both had psychology backgrounds. They both were very mathematically talented. Herb Simon actually was also an economist and ultimately received the Nobel Prize in economics for his early work on game theory. But they were very much also involved with problem solving and simulating problem solving, and became known as major AI leaders during that decade and beyond subsequently. John McCarthy had left MIT to go to Stanford by the mid-60s, but Marvin Minsky was there, and he had many very influential students. Marvin Minsky only died a few years ago, but and all of these people have now passed away. But Marvin was at MIT right till the very end of his career, with a huge impact on the field. And then John McCarthy moved to Stanford from MIT and retired there after many, many years and led a great deal of the AI research at Stanford, along with others who joined him over the years. So what was happening in medicine during that decade, the 1960s? Well, the main project, and the one that arguably started the AI in medicine and healthcare field, was something called the Dendral Project. It started in the 1960s at Stanford. The initial brains behind it was this gentleman on the left, Joshua Lederberg. Lederberg is a geneticist. He had just come to Stanford in the late 50s from University of Wisconsin. And at age 33, had just won the Nobel Prize himself in medicine and physiology. Became chair of genetics, the first chair of genetics at Stanford. And very soon thereafter, met and had discussions with a chemist by the name of Carl Djerassi. Djerassi was an amazing person who was also a novelist, wrote plays, wrote books, but he was also a world famous organic chemist and was instrumental in the development of birth control pills and hormone chemistry. So they knew each other, and then Ed Feigenbaum, a computer scientist who had been trained at Carnegie Mellon University and was at UC Berkeley, was recruited to Stanford. And Ed today is an emeritus professor at Stanford. Neither Lederberg nor Djerassi are with us any longer, but Ed is still alive. And then Bruce Buchanan, who I'll be mentioning in a moment, also is very, very much alive and very active to this day. Feigenbaum was a computer scientist. He recruited Bruce Buchanan to help work on this project that the four of them kind of created called the Dendral Project. So what was it about? The idea was, look, there are experts who know how to look at the mass spectrum of an organic compound and figure out from its chemical formula and the mass spectrum what its structure is. And this is incredibly important in scientific research related to organic chemistry. Djerassi provided that organic chemistry expertise. In fact, Joshua Lederberg actually did a lot of the programming in the early work. So he was a computer nerd, if you will as being a great geneticist. They came up with this system that used rules extracted from experts in organic chemistry to actually look at and interpret the mass spectral data from a compound that was unknown in an effort to try to identify its organic structure. Getting those rules itself was tricky, and later there was the development, largely led by Bruce Buchanan, of metadendral, which was a machine learning system that was supposed to look at a lot of examples of mass spectra and known chemical structures in order to infer the rules that would help in the future when dendral itself was trying to solve new problems. This kind of work and other work that went on at Stanford in the 60s and early 70s led Feigenbaum to recognize that there was something about encoding the knowledge of experts that gave tremendous power to computer programs and that were trying to solve these human level problems. And he felt that it had been shown, there's a quote from one of his papers from 1977, knowledge of the specific task domain in which the program is to do its problem solving is more important as a source of power for competent problem solving than the reasoning method employed was. So he became a major proponent of the importance of understanding expertise, getting that knowledge, encoding it in a computer, and writing computer programs that could manipulate and add to that knowledge over time in order to solve problems. Now, there were clinical medical programs that were started in the 1970s. I'm going to mention three of them because they're often mentioned together. And they were the ones that I knew very well during these early days. These all were developed between 1970 and 76, roughly. First one is known as Internist 1, later called QMR when it worked on PCs, Katznet, and the Mycin system. They all developed new methods that were subsequently used outside of medicine. So it plays to that point I was making earlier about how influential medically oriented AI programs actually influence the evolution of AI itself. So let's talk about each of them very briefly. Internist 1 took on the ambitious task of trying to provide diagnostic assistance to clinicians for all of internal medicine, all of adult medicine, later augmented by pediatric medicine. The brains behind this was a very famous internist by the name of Jack Myers from the University of Pittsburgh. He had been chair of medicine at the University of Pittsburgh, and many of his compatriots in internal medicine, when they gave up being a chair of medicine, decided they better write the next great textbook in the field. But what he would decide he wanted to do was see if he couldn't try to capture what he knew inside computers. He developed a relationship with a computer scientist at Pittsburgh by the name of Harry Popel, and he spent many years of his life working with Popel to try to encode what he knew about internal medicine in this program. Later, they were joined by a medical student who had an engineering background from Princeton and had come to Pitt to study medicine, Randy Miller. And Randy became a key element in the system. Eventually, he took it over after Jack Myers had retired, and had a huge impact on the way it evolved, and eventually worked on PCs. And in you can see 1982 in the New England Journal of Medicine, they wrote a paper on the performance of Internist 1. And they challenged it with a large number of the most difficult cases that had been published in the New England Journal of Medicine in a 2-year period. And these are called CPCs, or clinical pathological conferences, that are presented in a grand rounds, discussed by experts, and they know what the actual diagnosis was that was made from the pathologists. And they also knew the struggles that the actual physicians caring for the patient went through trying to figure out what was going on with the case. The remarkable thing about the paper, and one of the reasons it got published in the New England Journal, was that the program was as effective as anybody in diagnosing these very difficult cases from many fields within internal medicine. The only clinician, if you will, that performed better than the computer program and across these many cases were the people who were the discussants and who had studied up on each case in order to present them and discuss them at grand rounds. So very influential and impressive program with a lot of knowledge of medicine in it. The second system, Katznet, was developed at Rutgers University. It used a methodology developed called causal association networks. All the work was done with a ophthalmologist by the name of Aaron Sapphire. And they were trying to diagnose glaucoma and the various types of glaucoma by reasoning from observations that were made in the clinical setting to an understanding of the intermediate pathological states that seem to be present, and from those to infer the likely diagnoses. So this piece of work also was written up and heavily studied, and led to this whole notion of how associations and causality could be captured from the minds of human beings who understood these diseases, and then used effectively in new diagnostic challenges. So our work at Stanford, I was at Stanford in those days. This was actually my dissertation work. I was an MD PhD student at Stanford Medical School. My PhD dissertation advisor was Stan Cohen, shown on the left, who was not a computer scientist. He was actually the chief of clinical pharmacology at Stanford Medical School, himself a geneticist, as well as a clinical pharmacologist. And he went on to develop methods for gene splicing, for which he's very well known. But he was very supportive of the kind of work that I was interested in. And Bruce Buchanan became my colleague and mentor from the other side of the street over at the computer science department. And so Bruce helped me a lot, and we ended up developing a system that was designed to tackle the challenges of choosing antibiotics when patients presented who were very sick, but who you did not yet have full information from their cultures of either their blood or their cerebral spinal fluid or their sputum or what have you. Oftentimes you have to wait to get that information back, but you have to treat them in the short term. So there's a lot of clinical information that is brought to bear in deciding what antibiotics, if any, to give to a patient. So that was the task we worked on, encoding the knowledge of infectious diseases and treatment, and then providing advice to clinicians regarding the treatment options that might make the most sense. It was designed as basically 3 interacting programs, the system that actually gave the consultation to the physician, but also an explanation system that attempted to explain both why questions were being asked of the physician, how that information would be useful to its reasoning, and also at the end to try to justify the therapeutic recommendation. The consultation system used information that was provided by the clinician about the patient, observations that the physician made, and then a corpus of decision rules that were kept entirely separate from the program, which encoded the knowledge that I've been referring to of infectious diseases and treatments and diagnosis. The consultation system had to keep track of what it was doing, and the explanation system therefore had access both to a record of how the reasoning had proceeded and also to the rules themselves, and could use those to give explanations. And then we realized that experts who wanted to improve the performance of mycin could use the same system, run a case, use the explanation system, and potentially discover problems with its reasoning, things it didn't know that it should have known, and the like. And so there was a third program called the Rule Acquisition System that experts could use, and only experts could use, in order to write or edit the corpus of decision, or either new rules or edit those rules that were already in there if they needed to be enhanced in some way. So as you can see, there was this interesting combination of explanation and knowledge, which together required that there had to be a way to make the knowledge understandable to the person using the program. So although the rules were written using, a computer language, Lisp, such as this, it was relatively straightforward to write code that would take that kind of a rule and translate it out into English so that it could be understood by the clinician as an explanation for the kind of knowledge the program was using. So here's a very simple rule, and I'm not going to be able to talk about it today, but you'll see that there was also a recognition that not everything was absolute, that there was often a probabilistic concept or notion, and a great deal of thought went into what these numbers were and how they should be manipulated as part of this work. Now, at the time, the prevailing assertion was that clinicians would use AI systems if you could show that the programs could function at the level of experts. It was this assumption that led to them often being called expert systems, systems that tried to be like experts. So as I told you a moment ago, in the case of the Internist program, they tried to demonstrate the expertise that program had by running it against a bunch of cases, showing how it compared to human experts and clinicians, and then publishing that. And we did the same thing with mycin. This was a paper that appeared in 1979 in the Journal of the American Medical Association, in which the study design was to keep it blinded so that those who were making assessments of the quality of therapeutic recommendations for specific cases were not aware which recommendations were coming from a computer and which were coming from clinicians of various sorts. So this paper showed that mycin performed as well as infectious disease consultants at the task that was shown. And we were, of course, very pleased with that. And JAMA published it. But as I will be emphasizing as we proceed, I think that this earlier notion that I showed you that docs will use AI systems and programs or expert level contributors is simply not true. It's part of what needs to be true, but it in and of itself is not enough, and we'll come back to that. In parallel, there was a great deal of work going on in the psychological community to try to understand the nature of clinical reasoning from a psychological perspective. And much of that literature contributed to the work that was being done in the AI medicine community because it helped us understand the reasoning processes of experts. This book by Elstein, Schulman, and Spravka from Michigan State University came out in the midst of all this kind of work in 1976 and was very influential in the AI community. There was very important work that was done at Tufts, New England Medical Center, and MIT collaboratively in the area. And I won't go through the details of these people, but they were all very involved in collaborative work between doctors and computer scientists. And there was just a little bit later work by Vimla Patel at McGill University that also made important contributions to the evolution of AI in medicine research. So this is an attempt to tell you what was artificial intelligence viewed as then as compared to now. If you took out the textbook of Patrick Winston's textbook of AI in 1982, this is how he defined it. It's the study of ideas that enable computers to do the things that make human beings seem intelligent, but in particular, that they could reason symbolically, they could acquire knowledge, they could apply the knowledge, and they could manipulate and communicate ideas. I think today you'll find rather, shall we say, evolved definitions of AI that are much more focused on learning than was the case in those days. Well, this expert systems juggernaut really became very visible. They were covered in the lay press. There were a lot of medical examples used in Time and Newsweek and other magazines that wanted to do articles about this coming revolution. This is a book that Ed Feigenbaum wrote with some colleagues on the way in which companies were adopting AI and expert systems technologies and using them in their own product lines and internally for certain kinds of tasks. So it was definitely getting a lot of attention and arguably perhaps a little more attention than was warranted for something that was still rather young. So in the 1980s and 90s, as that expert systems juggernaut took off, we encountered eventually a kind of perception of overselling of artificial intelligence, that not all the predictions had been borne out, at least not as rapidly as had been predicted, largely by the press rather than by those doing the research. But the press had certainly gotten on board with this concept. And we began to see people avoiding the use of the term AI in their own work because it would be inappropriately come under the shadow that has sometimes been called AI winter, the period during which it was very hard to get funding if you were working in AI. People decided it was a bubble that had burst. And especially in the early 90s, I would say things were particularly complex in that regard. But I must say, the AI work continued. It's just that we called it other things. Suddenly people were building ontologies, or they were doing knowledge discovery in databases. And these were words that were sort of more acceptable, but it was all AI work. There had actually been, outside of medicine, an earlier AI winter in the late 1970s, but that's when AI in medicine was peaking, so we weren't so aware of that if we were working in the medical area, but we certainly were aware of the second AI winter, when the interest and enthusiasm declined between about 87 and 93. The interesting thing is that as things started to come back, that interest and enthusiasm has just continued on, and there has been a third AI winter. And one of the questions maybe we can address at the end is whether there's likely to be one, because there certainly is a fair amount of press interest and enthusiasm for and expectations of AI today that could lead to some disappointment. Computing in general is getting a huge amount of attention, including AI, during the 90s. You know, covers of magazines, a very young Bill Gates, but basically being portrayed very positively. And by the 1990s, by the early 2000s, we had medical specific, cover stories in the major news magazines regarding medical computing, and some of which was medical AI. But probably the biggest explosive change that occurred was, when all of these things, these paper records that had been the bane of everyone's existence prior to the new century, and they all started to get put into computers. So that explosive investment in electronic health records, suddenly digitally available data, sometimes pooled, certainly within institutions, but sometimes even between institutions. And so the EHR explosion in the 2000s, largely at the end of 2000, when we had the economic downturn, there was a big investment by the federal government in encouraging the implementation of electronic records. And then the work often ascribed to Jeffrey Hinton and others to develop whole new approaches to machine learning that allowed multi-layered neural network approaches of the sort that today we call deep learning. And then suddenly you had enough data to actually learn in ways that wouldn't have been feasible before, because the data were not adequate for the training purposes, but they became more and more adequate. And the techniques and the computing power made it all possible. So I would say, since 2005, 2006, machine learning has become an extremely important part, not only of medical AI, but of AI in general. And that's why we have, Siri and driverless cars and all the things that have been going on that have been very much dependent upon machine learning and image processing methods. Okay, with that history, I want to talk a little bit about clinical decision support and characterize three different major types. One type that has especially been influenced by artificial intelligence is the interpretation of data from medical devices. EKGs, X-ray images, EEGs, path slides, hematology slides, photographs of skin lesions. These programs tend to produce reports, and then the physician gets the report and often can look at both the report itself in one of these areas, and if they have relevant expertise, can determine whether or not the report makes sense and act on it accordingly. So the clinician can verify the interpretation, incorporate it into their own decision-making process, maybe even getting a consultant if necessary to assist. And this is a pretty well accepted concept, partly because the clinician still feels very much like they're getting information and then they are still in control. This is not a new idea. When I was a medical student, we were getting electrocardiograms like these. And gradually we began to see that the companies that produce electrocardiogram machines were able to actually write software, not AI usually, but rather signal processing analyses that would actually put an interpretation of the electrocardiogram right onto the EKG report itself. And of course, if you knew something about how to read an electrocardiogram, you could look at the actual tracing. This is very abnormal, and look at what it said and decide, yeah, that looks like a pretty good summary of what I'm seeing here. And so people liked that, but they still didn't feel that they were overly dependent on it. Now, move ahead until a few years ago, and we began to see articles like this. This one was a deep learning system published in the Journal of the American Medical Association about the interpretation of retinal photographs to diagnose diabetic retinopathy and other eye diseases. This one happened to be doing comparisons across different ethnicities. But there have been many such articles in radiology, retinal photography, electrocardiogram and EEG interpretation, and the like. So these are of that sort, what I call those class 1 type. They produce reports, sometimes in a way that requires expert interaction with the clinician who's caring for the patient, and human experts as well. Now, many of you in the HIMSS community certainly are familiar with the various kinds of event monitoring and alerting systems that can be built into our medical record and order entry systems. These are pretty typical. They're not very advanced. It's usually simple logic. But you have a repository, typically in EHR, for clinical information. You have some kind of interface to the clinician that they use for chart review or order entry. But in some systems, many systems, you have some kind of a monitoring software which watches what's happening as new data flow in about a patient into the EHR. And you have to have some kind of a knowledge base, typically rules of some sort. They may be very simple. They might be written in ardent syntax, for example. And it's a knowledge base of what to watch for. And if a rule happens to fire in a given case because somebody has all the conditions from that rule in their database, then you can add decision support, warnings or alerts or other kinds of guidance, noting that someone has an allergy, what have you. And the clinician gets that as part of their interaction with the chart or the order entry system. And the rules, as I said, tend to be relatively simple, simple conditional. Here, if you look in the EHR and you see the patient's on digoxin, and they also have a low serum potassium on their lab tests, then you should probably warn the physician that this person might need potassium replacement because of the chance of digoxin toxicity being aggravated in the presence of low serum potassium. I'm going to focus now for the next few minutes on the notion of direct consultation with clinicians, which is what, for example, Myson did, what Internist did. These were programs that were trying to actually interact directly with the doctor and help them solve a problem. And that's where, as I indicated earlier, we found there were major problems in gaining acceptance, even if the programs could be shown to function at the level of an expert. So imagine for now this kind of a system. You've got some kind of an advisory tool, usually for diagnosis or treatment. You've got some kind of analytical method that offers analyses to the clinical advisory tool. They could be rules or scoring function of some sort. They could be statistical. It could be machine learning. You have a physician who could use that tool, but that's the consultation model. That's where you're answering questions about the patient, and it's then running some analytical software on your answers. Physicians today don't want to have to put in information about the patient. They figure that the computer ought to know the information about the patient, because on the back end, they ought to be interacting with the EHR and getting as much information as possible there. Of course, if you have an EHR, that means you also have an interface to clinicians that could integrate the decision support function with chart review and order entry. So there are these two models of how physicians could interact. The consultation model, which has now pretty much been debunked, which we called the Greek Oracle model. You go to the mountain to get advice, but you have to answer a lot of questions and then you get the advice. This is much more integrated with your normal workflow. It can be much more efficient, and this is the preferred model. And in fact, essentially all consultation work today assumes that it's going to be through normal interactions with an existing system that you're using anyway. Now, there are a whole bunch of issues that arise in this context, and that's what I want to close out my time talking about. And rather than read them here, I will go through them one at a time. These are summarized in an article in the Journal of the American Medical Association in 2018 that I wrote with a colleague, Martin Sepulveda. And when you see CDSS on these next few slides, it'll be referring to clinical decision support systems, which could be AI systems, and certainly any AI system that purports to be giving advice directly to clinicians is a CDSS and would be influenced by these guidelines that we laid out in this article. So we talked about what you have to do to actually be effective in developing such systems. And based upon many years of experience, I believe that when you have a clinician interacting with a system that's giving them advice about diagnosis or therapy, that system has to be able to give them explanation for what it is recommending. So this black box is being an unacceptable criterion. It's coming up a lot now in machine learning, and I'll talk about that briefly in a minute, because machine learning systems, not being knowledge-based, often don't have a knowledge-based method for explaining their reasoning. Second, they have to be sensitive to the clinician's time. Basically, it has to integrate smoothly into workflow. If it takes a whole lot of extra time, no matter how good it might be in other ways, it will not be used. We know that complexity and lack of usability get in the way of use. And this seems obvious, but you'd be surprised how many systems are built without careful consideration of the usability aspects, even in industry, maybe especially in industry. I've been struck by how I see formal usability testing efforts often more common in research settings or development settings rather than in product development. Well, we know from experience that users will vote with their feet. If they don't like your design, they'll go their own way. It's intuitive. You can look at that picture and you say, well, of course, what a stupid design, right? Next one, relevance and insight are essential. We know how annoying it is if you're a male filling out some kind of a form and the computer asks you if you've been pregnant. It just shows that the machine is not in touch with the reality of the situation, that they're doing something pro forma and they don't know much. And there are many ways in which medical systems can demonstrate that they're not really well in touch with the reality of the situation. I love this one. I think if you look at this patient seeing a doctor, all of you can make the diagnosis of why this patient is not feeling well. So I love this cartoon for that reason. You know, rapid pulse sweating, shallow breathing. According to the computer, you've got gallstones. Well, the computer just doesn't know about this particular syndrome. It was never going to get it right, and is kind of out of touch with the reality of that clinical environment when that kind of advice is offered. Next is the whole issue of being respectful to the user of this system. You know, if you give the impression that you, the computer, are also the clinician, or think of yourself that way. There's an old cover of an AI magazine some years ago, you know, kind of showing this notion of the robots taking over the doctor's role, even in the operating room. So that's not the way these systems need to come across. They need to show that they have a real appreciation of the intellect and knowledge of the user, and that they are there to augment the user, not to replace them. So it's not that the computer is better than the human brain, but that the computer can augment the human brain in ways that allow the human brain to do better. And finally, and arguably even maybe most importantly, is that we in medicine have come to expect that innovations that are offered to us for potential use with real people in real clinical settings usually have valid data to support them in the literature, not just an FDA approval, but articles in the peer-reviewed scientific literature. And they need to look not only at the accuracy, the way that those early papers on Internist and Mycin did, but also on usability, reliability, acceptance, and the like. So a reasonable development plan and evaluation plan and implementation plan needs to bear in mind all these kinds of demonstrations that need to be done and ultimately written up. Maybe not all in one paper, but eventually. And I would argue that these last four are seldom written up, seldom in papers, and the emphasis in the research literature tends to be on the first two. So there's a simple diagram I can draw. There is basically initial work that goes on in the laboratory, if you will, or it may even be retrospective work. But these are, you can validate the advice by some studies that you do before it's ever actually used on patients. You can do formal usability testing on your interface. You can bring in collaborators who are potential users in the future, who can help you see through the problems in that usability problem. You can even get feedback about integration with workflow and observe to see how well it avoids disrupting workflow in simulated environments. And the core technologies can be validated individually as well. But then you need to do studies in the real world, the naturalistic settings, if you will. And you have to do them in order. It doesn't make any sense to go right to the end. You first have to show that they're acceptable to users. That is, that they use them. Then you need to show, if they do use them, does it change in any way how they behave? If it doesn't, there's not much point in going further, because if they're behaving the same as before, why bother to offer it at all? Only if it affects their behavior can you do formal studies, and this is where we might even imagine randomized controlled trials of some sort, but certainly very carefully orchestrated studies to try to show over time the impact that the system has on patient outcome compared to when you treat patients without the use of the system. And only then is it worth doing cost-effectiveness studies that ask the question, well, for the impact that it has on patient outcome, is it worth the expense? So I think there's some implications for this. Commercialization of these kind of systems requires a time-consuming staged evaluation plan that demonstrates much more than the quality of advice or of the interpretation that the computer program makes. And that early adopters naturally become partners in evaluation. And you need to think of them that way. They help you build the system, they help you test the system, and they may well be the first ones to use it in real clinical settings. And so this blending of the researcher with the eventual clinical users of the systems right from the beginning becomes crucial to getting this right. All right, so we're in the current decade, where we see this explosion of interest in AI and in medical AI, which is getting as much attention as any area of application in the press. We see a lot of confusion in terms, I find. AI, machine learning, data analytics, data science. These are not synonyms, but people sometimes jumble them up. I'm concerned because deep learning, I believe, is too often being viewed as the solution. That is AI today. All the rest of that stuff doesn't matter anymore. But as I intimated a moment ago, what does a deep learning system really know when it's performing well? It doesn't know anything of the form that would allow it to explain to you the basis. There's a lot of work going on to try to develop explainability capabilities in machine learning programs. And many of us believe that there is a merger to be made between the classical knowledge-based approaches that I described from 20, 30 years ago and the machine learning approaches to give a much more acceptable and useful kind of consultative interaction. Many of the other early challenges that we knew, in those early days still persist. Challenges with integration. We're doing better, but there's still challenges. Interoperability across various platforms. Standardizing terminology, getting better, still gaps. Ownership of data, always been an issue and still is today. And there are others that you could all name yourselves, I suspect. So to close, I think the key lessons are we should avoid being too quick to reject that knowledge is power aphorism that Ed Feigenbaum talked about in 1977. Knowledge still has a place in the AI of the present, and we know a lot about how to encode it and integrate it, and more of that kind of work needs to be done. I think that we also need to be guided more than we have been sometimes recently by an understanding of human beings, and especially acknowledged experts solve the problem. We need to recognize that promulgation and acceptance of medical AI solutions is going to depend on much more than the decision-making or analytic performance. It's all those other steps that I mentioned, and have to accept that AI projects have to be driven by a deep understanding of biomedical issues. That means you must collaborate with the true experts or users. And I think you need to perceive that the future is bright, but this is not the end of the line. We are still in midstream. There's so much still to do. It's a very vibrant field with lots happening. And there's much fun to be had in the work that goes on in the future. So with that, I thank you. I can stop sharing my screen. I'm happy to answer any questions. I will do that now. There we go.
Okay, thank you, Dr. Sherlife. That's like a very, very inspired presentation. And yeah, we just, as you said, we are just on the beginning of everything, and we should, remember what their history, and that's not something would happen in the past years. That has very rich history of the exploration. We have a couple minutes for questions, and please type questions in Q&A. There are a button on the very bottom of the screen, Q&A. Type your questions there, and okay, we already have one. And number one is, which domain in medicine will most likely benefit from artificial intelligence decision support systems?
Well, that'd be a kind of hard. I mean, right now, I would say the deep learning systems are having the biggest impact in various imaging fields, right? And are demonstrating tremendous accuracy and capabilities, almost like magic as well. Some people characterize it, So, and yet my former student and colleague now, Kurt Langlatz, has made the point that, AI is not going to replace radiologists, but radiologists with AI may replace other radiologists, so that the AI is going to become an important adjunct to that kind of practice. And I think that's true for many of these fields that involve that really benefit from the capabilities of the deep learning approaches. So right now, I would say, I just recently stopped editing a journal, which I've been editing for 20 years. And I can tell you that in the last few years, almost all the AI papers had to do with deep learning, convolutional neural networks, often with an emphasis on imaging or EEG analysis and the like. Very few having to do with the kind of consultation models that I've been talking about. So I think ultimately, they all can benefit from AI. And I wouldn't want to pick one. But I think if we look at where we are right now, the biggest impact is in imaging and other deep learning application areas.
Thank you. Yeah, there are another question actually is related to imaging. Can you address the litigation trajectory of AI or the lack of AI utilization? I work in AI in enterprise imaging. That's a question.
Oh, I see. Oh, the litigious trajectory of AI. Now, this is about the legal stuff. Okay. We've talked about this from the beginning too. And I must say, I've been aware that it immediately arises in people's minds. But if you design the systems right, the system is not making the decision. The doctor is making the decision. That's what the doctors want. They don't want the computer making the decision, but they are willing to benefit from an interaction with a computer that allows them to make sometimes better informed decisions. So I recognize that there are recurring questions about whether or not the AI manufacturers are going to somehow or another be liable, and perhaps they will, especially if something is sort of turned loose in a way that prevents a human being from intervening before something happens that's guided by an AI system, a closed loop system of some sort. But in the non-closed loop systems where there's a learned intermediary, I believe that the legal issues are way overemphasized. I see they disappear after I answer them. Is that right?
Yes.
Okay,
Yeah.
got it. Okay. Did I skip one?
No, that's one more question there.
All right.
Oh, that's another.
All right. How do you see reimbursement growing in this area? How do we move this process along? Well, I've never been one that believes that it's likely that you're going to get reimbursed for using one of these systems. I believe that you will have a cost structure for your practices and the like that will make these systems as important a part of what you do as a clinician as having access to the laboratory or the other kinds of facilities that you offer in the medical environment. If you can eliminate 3 unnecessary visits to see you, the insurers will be very happy, and they might be very happy even to pay a fee based upon the fact that you use something that was intending to try to simplify the patient's care or avoid an unnecessary surgery or whatever, or just provide a better outcome. But I think we're kind of reading tea leaves a bit here if we try to anticipate this too much. This next question is about bias in AI. Is that the one you want me to do next? Yeah, well, of course, this is huge. And this is much more of an issue right now in the area of machine learning, where the adequacy of the balancing and the creation of the training sets becomes important to determine whether there may be significant bias or related on social determinants of health, ethnicity, racial characteristics that are not adequately balanced, and you end up having a system that's been trained to do real well on white people, but not on everybody else, or on wealthy people, but not on the poor, what have you. And I think all the work that's been done to try to make sure that this is adequately considered in building the data sets, and all the articles and the literature I've been seeing on it has raised the consciousness about this, so that people are trying to be very careful in putting together the training sets that they use precisely in an attempt to try to make sure that they don't inadvertently introduce bias into it. It's an imperfect science. Sometimes you're introducing biases that never occur to you, and we'll learn from that more. But I think those really obvious ones having to do with imbalance with regards to demographics is definitely being considered in most work today.
There another question.
Is there a way to translate machine learning into human understandable knowledge? Well, that's a great research question, isn't it? I mean, I would love to see more work looking at that question, because if you could, right now, what do you basically say? Well, there are a couple of nodes 3 levels down in the neural net that have really lit up in this case, and that's why I think it's such. You can't explain it that way. So you have to have some way that you can assign some kind of knowledge-based interpretation to whatever is happening in that net when it reaches the conclusion it does about a given case or about a given image or what have you. And I've been interested in, are there ways of using some of the old knowledge-based approaches for representing knowledge in computers and integrate that in a way that allows it to interact with a machine learning system after it has reached its decision about a given case or interpretation of a given data set. If you search for the word explainability in AI, you will find a huge growing literature. This is not a future topic. It is a future topic because there are no good answers yet, but it is very much on the minds of many people working in the area of machine learning right now. So, I'm working on a textbook of AI medicine right now. We have a whole chapter on explainability as a topic of its own. So I think you will see a lot more about this. And it is a reason to critique some of the systems, because it's what they tell you, you have to take it or leave it.
We have a couple more questions. The next one is very tricky about IBM Watson. how you can comment on that.
Yeah. Well, IBM Watson wasn't a thing. It was a company, right? And it had lots of products. And by the way, I'm speaking as a former consultant to IBM Watson. So I saw a fair amount of it up close. I'm no longer working with them, but I saw them up close. But mostly what I was helping them do was some of this work I described to you regarding evaluation, how to evaluate those systems, because they didn't have a good feel for how to do it and get it published. And we spent a lot of time working on that. But the systems had varying amounts of AI actually in them. There was a lot of non-AI elements as well. And that's good. I mean, you want to use whatever method makes the most sense in a given setting and context. But it did have trouble, I think, partly because of not fully appreciating the clinician's perspective in the early days in getting as much buy-in as they would have liked. They had much more penetration. I shouldn't say past tense, it still exists, but in the days I was there, they had much more penetration into the international marketplace, especially Asia, where there was a lot of experimentation with Watson software products. Maybe the one that had the most penetration over there was Watson for Oncology, which helped you choose the therapy for patients not on clinical trials, established tumors, and not being put on trial. How can we avoid alert fatigue for some physicians? Some knowledge from CDSS may be not new for senior physicians. Well, I think that's an issue for those warnings and alerts that come up in the middle of evaluating a patient's EHR and the like. And I think you do have to be really careful not to overdo it, shall we say. I've seen a whole bunch of approaches to this. By the way, this is not really an issue for a consultation program. Consultation program, you've come to it and asked for advice, or for one of those first class, the ones, the vision processing ones, the image processing ones, where you ask for an analysis of an X-ray or a CT or an MRI or something. So it's a warning and alerts where I think we talk about alert fatigue. And I think people learn the hard way that they can overdo it, and then they learn to try to cut back, and also to try to, I think, and would be much more intelligent to really develop models of individual users and get a sense for what they know, what their expertise is, and maybe pick and choose the way you give your alerts based on who the individual is. But most of the platforms, the EHR platforms today that have simple alert capabilities, don't allow you to do that kind of thing. So it too is a product potential for the future. It's one of many places where I'd like to see the big companies, the Epics and Cerners of the world, interacting with and collaborating more with people in the research world and the informatics world to really think through and develop approaches to these problems that could then become integrated into the products. Because maybe I'm wrong, maybe there's something going on I'm not aware of, but I haven't seen that much in the product lines as of yet. Can we avoid black box AI in medicine? I hope so. That was what I was calling for. That's exactly why that was number one on my list of considerations. I as a physician would not use a computer that told me to do something and couldn't tell me why.
Yeah, we have one more question. Yeah, and
this one, there are lots of new tools and models for specific purpose developed, but application of machine learning models to a large scope is the biggest challenge. Any suggestion of accelerating the process of applying AI models and algorithms in practice? It's interesting, and maybe this isn't what you were thinking of, but I have found that med school education deans are suddenly really interested in how they can bring data science and machine learning capabilities into the curriculum in medical schools. There is this growing sense that you can't be a nephrology fellow if you don't know something about how to work with data, analyze data, maybe using deep learning, maybe using other machine learning methods. And that the more that actual clinicians feel comfortable with this and have real skills in the area, the more we'll see actual applications developing in greater numbers. So let's see if, I mean, I've been writing for 25 years about why I thought informatics needed to be part of the medical curriculum. It hasn't happened to the extent that I had hoped, but at a few places it finally really is. The medical college in Phoenix that you mentioned, Natalia, earlier, where I was dean for a while, was started with the notion that biomedical informatics should be part of the curriculum. It's one of the reasons I went there. I thought it was great to see a med school that thought that was an important part of what med students should learn. But I see I've run over, and I don't want to keep you any longer.
Yeah, that's probably, yeah, we are on the way over the time, and we should conclude for today. Yeah, thank you so much taking your time. That was amazing summary, and really I believe that would be inspiration for people who just entered this field to understand why everything there and what reason why we are all doing that. Thank you so much, and we appreciate your effort. Thank you.
Happy to do it. Thank you. Bye all.